website if you want to check it out. You'll see all of the speakers and all of the talks listed there. We also have a few items who seem to have lost their owners. So if anyone's missing your spectacles that was lost sometime yesterday afternoon, please come find us at the back of the room or at the registration desk, and it'll be there. And someone at the dinner left their notebook. We do not want to scoop your research ideas. So please, if you know of someone who mentioned this to you, also please let them know that they should come find us at the registration desk. Thank you. Now I guess we can start the session.
Okay, so welcome to the continuation of this morning session. So our first speaker is Ben Baragiola, and he'll talk about quantum computing with rotation-symmetric bosonic codes.
Hey, all right, this will work fine. So hi, my name's Ben. Thanks for having me here. I am at RMIT University, which is in Melbourne, Australia, but this is a picture of Albuquerque, New Mexico, where I'm from and where I did my PhD, and a lot of quantum information scientists passed through UNM and New Mexico and Santa Fe at one point in their career. It's a beautiful place. So I'm going to be talking about quantum computing with rotation-symmetric bosonic codes, and I think more generally I'm just going to give you a pitch for why you should care about bosonic error-correcting codes to begin with, as an alternative to qubit error-correcting codes at the bottom level of a concatenated fault-tolerant quantum computer. So the work that I'm talking about was done with Arne Grimsmo and Josh Coombs, who are both also in Australia now, even though Josh is kind of still affiliated with Rigetti Computing. So as we heard yesterday, I think, the primary resource for quantum computation is Hilbert space dimension. And that applies for performing quantum algorithms and doing any of the tasks you'd like to do on your quantum computer. But even more so, in the presence of noise, we need this Hilbert space to do quantum error correction. So the standard approach is to get this Hilbert space for error correction from a tensor product of a bunch of qubits, or finite dimensional systems. And you build your error-correcting code by spreading your logical information in clever ways across your physical qubits, such that you can use the excess Hilbert space for error detection and correction. An alternative approach is to use physical systems that have an infinite dimensional Hilbert space to begin with. So bosonic modes include things like the quantum harmonic oscillator that we're all familiar with, and shown here are some of the ground state, or the ground state and some of the first few excited state energy levels, and associated wave functions. So we can, when talking about a bosonic mode, describe things in terms of its energy eigenstates, which are infinite but discrete and countable, or in terms of wave functions, which are written down as superpositions over some observable that has a continuous spectrum, like position or momentum. But no matter how we construct an error-correcting code, we have to answer these questions below, notably the last one. So typically we go through a lot of trouble and potentially very complicated operations to encode and perform error correction. And at the end of the day, we want to make sure that we have reduced the error on our logical qubit by all the crazy stuff that we've done. So the idea of a bosonic error-correcting code is you pick two wave functions, and they're going to provide the projector onto the logical subspace, and the rest of Hilbert space is useful for error detection and correction. There's kind of foolish ways to do this, or not kind of naive ways to do this. You could imagine encoding as your logical zero, your zero Fock state, your lowest energy eigenstate, and your logical one, your one Fock state. That's fine as a code. You can put the information there, but it doesn't allow for error correction. So there's much more clever ways to do it that allow you to get an error-corrected qubit within a single physical system. And this is totally different from qubits. Obviously, you could not get an error-corrected qubit with a single qubit. So the whole idea is we have some errors on our bosonic mode, which I'm calling CV for continuous variable errors. In practice, if you're talking about an electromagnetic mode, the dominant noises are loss, heating, dephasing. Of course, there's other noises as well, but these are all errors that act on the full bosonic mode. And the idea of a bosonic code is you're going to project the CV noise into noise into discrete errors on the encoded qubit, which you can then concatenate with higher order qubit codes, and we've got plenty of those, to turn discrete errors into further discrete errors. So there was a nice review paper that came out last year about a whole bunch of single-mode bosonic error-correcting codes in the literature, and they've been around for basically 20 years, and there's a whole bunch of them. But I broadly classify these codes into two different types. Codes that are based on discrete translation symmetry, and codes that are based on discrete rotation symmetry. And of course, these are not mutually exclusive. And in fact, the translation symmetric codes, which are usually referred to as GKP codes for their creators, the physical manifestations of these code words don't actually have translation symmetry just because they're required to be normalizable and have finite energy. But they're approximately so. In any case, I'm going to be talking about codes that have various degrees of discrete rotation symmetry. So in 2016, there was an experiment at Yale where they did an encoding into a so-called cat code. A cat code has code words that are composed of superpositions of coherent states around a ring with different phases. And they were able to demonstrate, I believe for the first time across any system or any type of code, full quantum error correction. In other words, they encoded a qubit. They let this encoded qubit evolve under noise, and they performed active error correction, decoded, and afterwards found they did better than just encoding into some trivial encoding. And that is a type of rotation-symmetric code. So I'll give you a constructive way to build one of these codes. It's all based on this discrete rotation operator. So we pick a positive integer n, which is going to set the level of discrete rotation symmetry in our code. And we enforce that our code space, so all the code words, are +1 eigenstates of this discrete rotation operator. So it's very much like a stabilizer. So here's how you do it. So this is for a particular case of n equals 2. And you can start with any state you like. I chose to represent it kind of as a blob, which could be a coherent state. So let's say I'm going to create a cat code now. But in general, it works for any primitive with some restrictions that you can ask me about later. And to create the logical 0 code word, you just superpose it around a ring. And for the orthogonal computational code word, you simply put -1 phases on every other lobe. And this makes them manifestly orthogonal. Since we have a set of orthogonal computational basis code words, we can construct dual basis code words without any trouble by superposing them as usual. And these are also exactly orthogonal. Now, in the literature and in experiments, some cat codes work with non-orthogonal code words. You can ask me about that later if you want, but you can construct orthogonal codes, so perfect codes. And you notice here that in the dual basis, the plus and minus code words are connected by a simple rotation by half the rotation symmetry of the full code. So it's clear that doing a logical Z is quite easy for this type of code. And you also notice that a rotation is never going to turn a 0 into a 1, as you hope. So since I haven't told you what type of primitive to use, there's a whole lot of freedom. And this generates a whole class of rotation-symmetric codes. The cat codes on the left, and the binomial codes, which were not initially kind of described in terms of rotation symmetry, are also rotation-symmetric codes. Additionally, you could imagine squeezing the cat codes before you superpose them. And we introduce a new type of code, which is based on Peg-Barnett phase states. And I won't talk any more about that, but you can ask me later. So just so you know, on the top, these are the cartoons. On the bottom is the Wigner function for the 0 state. So you can see there's a whole lot of interference going on as well in these superpositions. So we have an alternate description of states. We can look at phase space, and we can also look at Fock space. And we have this neat property that enforcing discrete rotation symmetry implies that our code words and our code itself has some sort of spacing in Fock space as well. So for the n equals 2 codes that I showed you 2 slides ago, you see that the code space itself is only defined on the even Fock states, with each code word on every fourth and an offset between the two. And this is what gives these type of codes resilience to number errors, such as loss. So a loss error takes you down one step on this Fock ladder, but it doesn't necessarily lead to a bit flip error. And the higher the order of discrete rotation symmetry, the further spaced these code words are in Fock space. So you can see there's this trade-off between resilience to rotation errors and resilience to number errors. And then again in Fock space, discrete rotation symmetry sets which Fock states you have support on, and the specific primitive you use specifies these amplitudes here. And you notice that because of this, doing a logical X operation, single qubit X operation on this encoded qubit is going to be quite difficult because you need to do a particular shift in Fock space. And if your code words have amplitudes, you also have to like reshuffle the amplitudes so they match with the original code words. That's quite difficult, which is why we'll avoid doing logical X entirely. So just visually, here's the phase-space representations of these states and the Fock space amplitudes. And the one on the right are these Peg-Barnett phase states, which have equal amplitude on all Fock states. And when you put them in superposition, it just cuts out the ones that aren't on the proper Fock grid. So you can imagine that the other codes we're looking at here are just envelopes on one of these Peg-Barnett codes where you extend it to infinity. This is kind of just for people who are familiar with GKP codes to make you start thinking about the analogies between the two types of code. So we've got these two descriptions that allow us to see visually that these type of codes can be resistant to number errors and phase errors, which are the dominant types of errors in like electromagnetic modes. But there's also one other neat thing which was recognized recently. These two papers came out within the last 2 months, and they recognized that if your dominant noise source is, say, loss, and you have much more loss than you do any other type of noise, then at the logical level, you have hugely biased noise. So loss gives you bit flip errors, but never gives you phase flip errors unless it's extremely high. And of course, you want your error correction to kick in before that happens anyway. And you can use this fact to concatenate with codes that are designed to protect against this strong type of logical noise, which is the proposal in the first one, taking the cat qubits and putting them into a simple classical 3-qubit repetition code. So we can perform measurements on these qubits, rotation-symmetric qubits, straightforwardly. Photon counting for undamaged code words, of course, will always give you a value on this Fock ladder, and you just need to match it up to determine whether you've got a logical 0 or 1. And in the X basis, you do phase measurements. And here's where things get a little interesting. So the phase measurement will always have some embedded error, meaning that even when you have perfect pure states, there's always some error that could convince you that you have like a plus state when you have a minus state. And it's due to the primitive that you chose. And this is, unfortunately, this is always the case with bosonic codes. With physical GKP codes, you get the same thing. There's always a little bit of squeezing noise, which leads to misidentification. That's all right. We can deal with that with error correction, assuming it's small enough. So we're going to use this universal set for quantum computation, where on the left, these operations allow us to do the Cliffords. So this is preparation of plus states, measurement in the dual basis, so this phase measurement, square root of z gates and controlled z gates. And we can teleport the s gate, the square root of z gate, or we can enact it unitarily, assuming we have access to a self-Kerr interaction, which is an n-squared type interaction. And we didn't do this because they preserve noise bias, but it turns out that this gate set does, as described in this paper down below. We chose this gate set so that we don't have to do these troublesome X operations that involve shifts in Fock space. Now, interestingly, this entangling gate that we use is a rotation-controlled rotation gate. So we call it a CROT. So the CROT gate is interesting because it allows you to interface codes of different rotation symmetry and different type. So by tuning this interaction parameter, you could interface, say, a cat code with a binomial code. It's agnostic to the code type you use. And again, we need to choose code words that have low embedded phase error, which is the same thing as approximate number translation symmetry. So the flatter the distribution in Fock space of these code words, so that we get good phase measurement resolution to do our X measurements. So with the Cliffords, we can do error correction. And again, the whole point of CV error correction is to discretize these CV errors and project them onto Pauli errors. But there's one other really neat and different thing about bosonic codes, which is that when you do error correction, you do a measurement that tells you about your errors in the Z basis, and you do a measurement that tells you about your errors in the X basis. And for qubit codes, the outcomes of these measurements, which we call syndromes, because they diagnose whether or not there are errors, are integers. For bosonic codes, they're real numbers. And there's a lot more information in a real number than in an integer. And this has been used in these two papers below to improve the performance of a concatenated qubit code on top of the bosonic code. It's very interesting, and ask me about that later if you're interested. But again, in order to do the corrections, we're going to have to do these troublesome Fock space displacements that we don't want to have to do, so let's just not do them. And the way we get around that is by doing teleportation-based error correction, which was proposed by Knill long ago. And the idea is, on the top rail, we have our data qubit that is potentially damaged, has undergone some error. We couple it via appropriately tuned CROT gates to fresh ancillas. And the two fresh ancillas on the other rails can be in any code of any rotation order. And what this circuit does is it projects the state on the data rail into the code on the fresh ancilla on the bottom rail. And it does this at the expense of a potential encoded Pauli error. And it's your job, using these two measurement outcomes, using the syndrome and some decoder, which is, there's not a whole lot of work been done on decoders, but use the decoder to determine whether there's been a Pauli error, and you can correct it if you can, or you can just keep track of it in software. So how well does this scheme work? We did a set of numerical simulations where we encoded a qubit. We encoded a qubit into one of these rotation-symmetric codes, specifically cat and binomial codes of various orders of rotation symmetry. And we subjected the data rail to equal amounts of loss and dephasing, described by this master equation above. So what that means is we let the data qubit undergo continuous dynamics under this master equation for some amount of time. So we have a total noise strength, kappa t. That's the x-axis of these plots. Then we perform this teleportation-based error correction, decoded, and we look at the fidelity between the input state and the output state. And you can see that, maybe I should mention, the comparison that we make is to doing an encoding into this trivial encoding right here, with no error correction at all. And this is the way the experiments are done as well. So that's the benchmark. Anytime you're doing better than break even, then your error correction is actually doing something useful, and you might want to implement it in your laboratory. So we can see that for various levels of noise strength, we're well below this break even. And in fact, you can compare this to the optimal recovery map that can be found numerically. And while these aren't overlapped with one another, they're on the same scale. So you can see that our explicit procedure performs very near optimally. So that's all I'm going to talk about right now. Obviously, there are some things that I didn't talk about, and some really critical missing pieces if we want to do fault-tolerant universal quantum computation. And the main one is state preparation. So we need to be able to produce fault-tolerantly high-quality plus states and high-quality magic states for universality. In addition, right now, Arne and one of his students at the University of Sydney are looking at a more systematic study of error correction performance under different noise channels, and also when you have noise on the ancilla as well. They were noiseless in the initial simulations. Something that I'm really excited about, and we're working on at RMIT with Nick Menacucci, who's my supervisor. I'm a postdoc, by the way. And one of our grad students is an explicit description of bosonic codes as subsystem codes, which is probably different than what you think of as a subsystem code. But I'm very happy to talk about it afterwards. It's really cool, and we should have something in the archive soon. And finally, I didn't get to talk about it because it's kind of a separate result, but we have another paper on the archive where we showed that for GKP codes, which are these translation-symmetric codes, it turns out that the vacuum state is a magic state. And this is a really surprising result, and completely makes obsolete something called a cubic phase gate, which was in the original GKP proposal for universality. So that's it for today. Good, right as the done pops up. So yeah, I can take some questions if you have any, or you can come talk to me afterwards.
Okay, thank you, Ben. So we have 5 minutes for questions. Any questions? Ken? Hey.
Hey.
Anyway, I'm curious about the this problem of preparation. And could you say a little bit more about how you think? I mean, I know, for example, Chris Chamberlain recently put out this thing to show preparation, which is fault tolerant to a single fault. But
yeah,
are you willing
right.
to share some ideas about how to make it more fault tolerant to a larger distance?
Yeah. So the problem with all the bosonic codes, so that was for GKP codes. The problem is that you need these really exotic states, and you need to prepare them well. And as far as I know, that is the only proposal that discusses fault tolerance at all. And to be honest, we haven't gotten into that yet. Most of the proposals involve coupling to, say, a qubit or some finite dimensional system in a particular way, measuring that qubit, which then projects you into this nice superposition, let's say, of cat states or of squeeze states if it's a GKP. But with respect to fault tolerance, not much has been done.
Thanks.
More questions?
Although, let me mention that this year is getting, this year is getting really exciting because, there was an experiment back in 2016 with error correction in cat states. This year, people have, for the first time in the motional mode of a trapped ion, prepared GKP states, and have also done binomial codes in superconducting microwave cavities. And I hear there's a rumor that Yale has also done GKP states in microwave cavities. So this is like the year that, what did Steve call it, like takeoff for bosonic codes. And it's kind of a niche field, so like if you're interested, it's a cool thing to get into. You can speak, sorry.
Yeah, more answers or more questions? Okay, maybe I could ask one. So
Yeah, sure.
Is there maybe a way of setting this up, the whole thing is sort of some sort of an optimization problem with, some sort of constraints?
Oh,
and some
totally.
optimization, and you'll just find your best sort of encoding and your best
Yeah.
universal set,
Yeah.
and then you're sort of done for every set of assumptions?
So this has been done with the constraint being the type of noise. So people looked at the optimal code for loss. If you had just loss errors, and it turns out the optimal code is a hexagonal GKP code. And they did this numerically. They started with a random code, did some iterations, and it converged every time to a hexagonal lattice GKP code. So yeah, one can do that. But it may not be a code whose operations are easy to do. Fortunately, GKP is. But if you had a more complicated noise channel, you might just get some wacky code that you don't know how to manipulate.
More questions for Ben? Well, since we started a little late and since there are no more questions, maybe let's thank Ben again.
Thank you.